Okay, so welcome to another catch-up video with me and Sylvain Munaut, Sylvain TNT Munaut. And Sylvain's been working on the tiny tapeout multiplexer. So for tiny tapeout 1, 2, and 3, we're using the scan chain, which has some limitations, slow, for example. And a bunch of people interested in it, in helping out, kind of did some thinking, and we came up with a multiplexer architecture, which has a lot of advantages. And if you want to find out more about that, then check the previous video that I'll link down in the description. So today is part 2. How are you doing, Sylvain?
Hey, hi, Matt. Doing well, thank you.
Yeah, it's cool to see you in Belgium. Thanks for helping out with the workshop.
Yeah, you're welcome.
Today, so the first time the first part of the project was the functional model. And then the second part of the project, which you completed a little while ago, is translating the model into hand-coded standard cells. So let's just talk about what the difference is between just having a functional model and hand-coded standard cells.
Yes, so in the functional model, we basically just use standard Verilog and rely on the synthesis tool to actually implement it using whatever cell is available in the PDK. Obviously, the nice thing about that is that it's easier to write and it's easier to read, and you can retarget it more easily. The downside is you're kind of subject to whatever the synthesis tool can do, and the result can vary. So, for instance, if you implement the mux for tiny tapeout 4, and then you do the same for tiny tapeout 5, you could end up with completely different cells just because the tools have evolved in the meantime and that kind of stuff, which can make it hard if you want to have like very consistent results, for instance. The other reason we're doing it is because in a further step, we'd actually like not only to control which cells are used, but also where they are placed exactly in the various blocks to try to control timing a little bit better, and again have more consistent results both between the blocks on the same chip, but also across different run of tiny tapeout. And if you want to place the blocks, it's much easier if you actually instantiated them yourself, because then you kind of control what name they will end up having in the file. While if you rely on synthesis, like those names are going to be automatically generated and random, it's going to be much harder to manually place things. So those are the two main reasons. There's some kind of auxiliary reasons, which is like deal with some potential limitation of the tools. Like, for instance, the handling of the antenna diodes in the tools. Currently, there is some uncertainty at what's the best way to deal with that. When you need to protect some lines across different level of hierarchy, because in tiny tapeout we harden blocks independently of each other and then just wire them up at the top level, but you still need to run the antenna analysis globally, I would say, and I'm not sure how the tool handled that. And so here we manually instantiate the diodes for all lines that go in and out of the blocks to make sure that they are protected at the cost of a slightly increased capacitance and slightly more area used. But it's better to have a chip that works slightly slower than having a chip that doesn't. So yeah, I think those are
Understatement of the year.
Yeah.
Yeah. So one of the things that I thought was really cool about your approach as well is you have a hardware how do you call it? Hardware abstraction layer.
Hardware abstraction layer, yes.
Yeah.
So instead of directly taking, if you instantiate a Sky 130 cell directly, in the TT control block or in the TT Romux block, for instance, you're kind of stuck with Sky 130, right? And so the way I did it is simply try to look up both currently only in Sky 130 and in GF 180, what were the primitives that were in common or were at least similar enough that we could use them, and define those as primitives. And then I kind of use those primitives instead of instantiating the blocks directly. And that makes it easy to retargets a different PDK in the future is that you don't need to go deep inside each of the blocks. You just need to look at the primitive. Okay, what do we expect that thing to do? And the kind of primitive is like an AND gate or tri-state buffer, that kind of thing. And then you look up the name, and then you just implement it. And you also have, like, actually in the implementation, there is currently only 2 variants. There is the Sky 130 variant, which uses the Sky 130 cell, obviously, and there is a generic variant, which is basically generic Verilog construct, which is mostly used for simulation and behavioral simulation, and to validate that the behavior with the standard cell, manually instantiated, matches the behavior that you actually want to have, and that allows like some comparison.
So, yeah, in a way, that's like a gate level simulation, even though it's like pre-synthesis.
Yeah, exactly. It doesn't include the delays, so you don't get like the timing from that standpoint. However, because most of the design of the mux is purely combinatorial, there's no synchronous logic. The delay will just end up being, end to end from the chip IO all the way to the user module, and so we can't estimate it with that model, but we don't have any problem of not meeting setup or not meeting all time or that kind of stuff.
Because there's no sequential logic.
Exactly.
Yeah, and that's actually another thing that I appreciate about the way that we're doing this is, like your comment on, if we had just Verilog and then we hardened it, and the things get placed where they are, and then maybe the tools change, and instead, like Yosis kind of does a different optimization. You get this mux instead of that mux or whatever. Every time we stand to have like these slightly different timings. What I really would like is we do our prediction of the timings with STA, and then we can also measure them, and that can go in the data sheet, and then that will just stay the same for all the runs. So that
exactly.
if you're doing something complicated, or you're talking to a memory, or you're doing something that's more performant, with driving a video controller or something, you can actually know how long it's going to take for a signal to get in and out.
Yes. There might be some difference across, where the block is physically located on the chip. Because although
we can have high-priced fast blocks and then like a discount for...
Depending on how... so the number of gates, I will say, like buffers and mux, is the same for each block. That stays constant. But obviously, the nets, the wires themselves might be slightly shorter from one to the other, depending, you have the vertical spine and the horizontal spine, as explained in the first video. Obviously, if you're like very close to on the beginning of the spine, you might get the signal like a tiny bit faster. But I don't know how much that's gonna represent really, because you still have to charge the whole net basically, because the capacitance is the same no matter where you are, and also it's something that we can potentially measure and characterize. If the first tiny tapeout that uses that mux is not fully used, we can place a few just loop back blocks in a few corners of the chip, and then we can actually measure the difference and what kind of span of delay we get, and how that matches with our simulations.
I really like that idea of having some test blocks that are kind of, you're reliant on, that they're always there, and you can make some measurements from them. One thing that we spoke about last week was, how is it possible to measure like the input versus the output delay? Because that's a bit tricky, isn't it?
Yes, I actually still don't have actually confirmed solution for that.
Just state the problem, because
that's what I was going to say. So to try to explain the problem is that, okay, if we want to know the delay from how much time it takes from the signal to go from the input pin on the actual chip package to the input pin of the user module, and symmetrically, we want to know how much time it takes for an output happening at the chip module, the user module, to go all the way from the inside block all the way through the muxing and IOs to the outside of the chip. How do we measure that? Because if we just put a loop back connecting input to output, we can measure the sum of those two delays. But we don't actually know how much of that delay is input, how much of that delay is output. And the other question is, the question is, can we measure them at all? And also, does it matter at all in the end? Does that actually have any impact? Because if all the input delays are matched, any kind of delay between the pin is going to be similar, including a potential clock, which means it doesn't really matter how much is input and how much is output. And so that's kind of the problem, or rather, like the theoretical question that we pondered last week.
To be confirmed.
Yeah.
Okay. So anything else you want to mention about that part?
No, I think it was pretty straightforward. I think you mentioned that someone was going to have a try at actually verifying and formally certifying that it does what it says it does, which would definitely be nice. But yeah, this step was mostly like preparation, really, for step 3, which is going to be much more involved, because at the moment, this hasn't really touched open lane and the hardening process yet.
No, it's all
the only thing that has used it is kind of the simulation, because I have simulated it with the models provided by the PDK, but that's really just taking one very, very log file and including it in the simulation. The next step is going to actually run this through the tool, check what they output, and then somehow find a way to guide them to do what we want. And that's proven challenging in the past, so we'll see how that works.
Yeah. One thing, we can cover this more in the final third part video once that work's been done. But how do you place like a standard cell exactly where you want it if you're using the digital tools?
So all the tools, when going through the various step of the process, you have this kind of def file, DEF, and LEF file, that kind of defines what cell exists and where they are. And so you can kind of inject yourself somewhere before the global placement step and take those cells and basically give them literally X and Y coordinates where they are, like on which row they are and on which kind of column. There's kind of a unit system, and if you're aligned to the grid, and then you just set a flag that say, okay, that has been manually placed, don't touch it.
Don't touch it.
Yeah, exactly. And then you can also let
the router will still do the routing.
Yeah, exactly. You can still you can do both if you want. You can also using that API, you can also find on the cell where the input and output ports are, and then you can literally draw wires, basically. And it's not that hard, I will say, because a lot of there is this API called OpenDB, I think, which you can control both in Tcl and in Python. And you can give coordinate XY. I want a wire to go from there to there, and then you can tell him to change layer, for instance, and then go up and that kind of stuff. And it will actually automatically generate a net of the like a metal rectangle of the appropriate width. Also generate the vias and all of that for you automatically, and you literally just draw X and Y of where you want the corners to be. it will not run DRC. So if you make two wire cross themselves, it will happily do that and short circuit them. But hopefully, if you do that, that will be caught later on during the LVS.
LVS, yeah, and also load the load the GDS and check it.
Yeah.
Okay, great. Well, thanks so much for your time, Sylvain. And looking forward to getting the final part done.
Yeah, definitely.